Good evening, everyone. I am M. Sai Krishnamurthy, Assistant Professor in the Department of Information Technology at Malareddy College of Engineering and Technology. I am delighted to be a host for this evening. It's my privilege to extend a warm welcome to all of you to the fifth day of AICT-sponsored six-day Atal Faculty Development Program on Next-Gen Solutions for Medical Challenges powered by AI-based intelligence systems, organized by Department of Information Technology at MRCET. Without any further delay, let's start today's session. It gives me a great pleasure to introduce our esteemed speaker for this session, Dr. G. Srinivas sir. Dr. G. Srinivas sir is currently working as a professor in the Department of Computer Science and Engineering at Gitam University, Visakhapatnam. With over 20 years of experience, sir has made a significant contributions in the field of computer science and engineering. In his remarkable career, sir has guided several research scholars from the reputed institutions like Andhra University and Gitam University, three of whom have already been awarded with the PhD degree. Sir has published a textbook titled Handbook on Android App Development in year 2020, reflecting his dedication to advanced technological education. Behind academics, Dr. Srinivas sir is an award-winning educator, having received the Best Teacher Award from Gitam University in the year 2010. Sir has made a significant research contribution, which includes 35 papers in international journals indexed by Scopus and SCI, along with 12 conference publications. As a reviewer for the esteemed journals and conferences organized by Sage, Springer, and IEEE, Dr. Srinivas exemplifies a community to lifelong learning and professional. Dear all, please join me in welcoming Dr. Srinivas sir. Welcome, sir.
Thank you very much, sir.
Thank you, sir.
So in the last session, we have seen about bagging, boosting, and stacking techniques. And also we have seen the implementation of bagging technique in the last class. So but due to the lack of time constraint, we have not seen the implementation of boosting as well as stacking. And today also we need to discuss about somewhat lengthy concept like optimizers. So what we will do is that we will first, I think the participants is also 58. We will start up with the explanation of the execution of boosting as well as stacking. So this is a single program for both boosting as well as stacking. So in the same Google Colab window, I have written both the program for stacking as well as for boosting. So I clearly explained you about the concept of boosting in the last class. So first of all, we'll execute the program with boosting. So you already know that in case of boosting technique, what we will do is that whatever may be the training data we have. So whatever may be the training data we have. So we are going to do the training process, or we are going to give the entire training data to one model. So as we have some kind of ratio like 80:20, 80% of data we are using for training and 20% of data we are using for testing. So 80% of data we are giving for, as the training for the model. After training the model with 80% of data, we are going to test the model with the remaining test data, 20% of data. So what actually happens in this case is that some of the samples will be predicted correctly, whereas some of the samples were not predicted correctly. So those samples which were not predicted correctly, we are going to give those samples to the next level machine learning algorithm. Here, instead of using only a single machine learning algorithm, we are using combination of machine learning algorithms. Means the machine learning algorithm is same of same kind. Preferably we'll use decision tree algorithm. So whatever may be the samples, first time they are not predicted correctly, those samples will be given high priority, and those high priority samples are being trained with the model with the previous trained data. So again, we will do the prediction, and whatever may be the samples that are predicted correctly will be given less priority or less weightage. And in the second level also, whatever may be the samples that were not predicted correctly will be given to the third model. So likewise, what we are going to do is that we are going to boost the models. The same kind of machine learning algorithm, instead of using one time, we are using for multiple times. So that is the idea behind this particular boosting strategy. So here actually, in case of boosting strategy, I am going to use a boosting technique called as ADA boost technique. So clear. So in this case, what actually we will do is that we will use one kind of ADA boost technique, and the same kind of algorithm we are going to execute with a single decision tree algorithm. So if you use a single decision tree algorithm, whatever may be the accuracy you are going to get, that accuracy will be definitely increased if you are going to use an ADA boost technique or a boosting kind of technique. So here in this case, this is a simple program because it is not that is there is no time for us to execute very big programs. So that is the reason why I'm taking a simple data set that is nothing but the breast cancer data set. Straight away, I'm having this particular data set in the sklearn. So that is where right away I'm importing this load underscore breast underscore cancer data set. And in this data set, what I'm doing is that I'm giving this entire data set to two variables. One is X and the second one is Y. So whatever may be the independent attributes we have, all the independent attributes are going to be stored in X, and the target attribute is going to be stored in Y. So that is the reason why we are taking two attributes. So one is for independent attributes and the second one is for the dependent attribute. Then actually what I am doing is that the second line, so I am executing each and every part. So it will take some time to execute because this is the first time today we are executing the collab. And see the second block. In this block, what I'm writing from sklearn.ensemble, because it is an ensembling technique. Basically, we are using ensembling technique to increase the accuracy of a model when you are getting low accuracy with an independent single machine learning algorithm. So whatever may be the machine learning algorithm it is. So the second case is that from sklearn.ensemble import ADA boost classifier. Because here we are seeing the implementation of boosting, I am importing a classifier called as ADA boost. There are so many boosting techniques that are available, XG boost, stochastic gradient kind of thing. So there are so many boosting techniques that are available. You can use any kind of boosting technique. Here I am using the ADA boost technique. So this boosting classifier, and I'm using n estimators is equal to 40. The meaning of n estimators is equal to 40 means here we are using 40 decision tree algorithms in the ensembling technique. I already told you that instead of using one machine learning algorithm or one decision tree, we are using multiple decision trees. Here the estimators are nothing but the hyperparameters. So hyperparameters are the parameters which actually use to increase the accuracy of the model. So instead of using only a single decision tree, here I'm using an estimator is equal to 40. There is no restriction that you have to use only 40. You can use any number of estimators. So here I am going to implement the boosting technique with 40 decision trees. Is it clear or not? This is the meaning of this particular thing. So I'm using an ADA boost classifier which is going to be developed with 40 decision trees. Then coming to the case, the next step is nothing but we are going to divide the data set into two parts. One part is the training part and the second part is the testing part. I am splitting the data into training as well as testing. I am executing each and every block. Right now I have executed the second block. Otherwise, you can keep all this data in one particular block and you can execute that particular block. And coming to the case of third block, what will actually happen is that we are going to split the data into two parts, training as well as testing. So here we are using a command called as stratify. Stratify means it is going to divide the entire data set into a ratio of 70:30, where 70% of data is going to be used for training and 30% of data is going to be used for testing. So I am executing this particular block. So after executing this particular block, I got an accuracy of 94% with ADA boost classifier. So if there is no boosting algorithm, if I am directly executing with the decision tree classifier that was there in the last block, without using ensembling technique, I am going to execute this particular program with a single machine learning model. See what is my accuracy. See here it is 92.30. So if you are executing the same program with a single machine learning algorithm, it is 92.30. So means the accuracy is only 92.3%, but using the ensembling technique that is nothing but ADA boost, you are getting an accuracy of 94.4. You can change this estimators also. You can take this estimators as 60. Once after changing this, you can execute the block. Previously, the accuracy is 94.4. So see that the accuracy will be 95.8. So here you are increasing the number of decision trees in case of ensembling technique. But there is no restriction that you have to use only this number of estimators. You can use any number of estimators. But even though in some cases what will happen is that after reaching a particular point, even though if you are increasing the decision trees also, there will not be any change in the accuracy. That will be our saturation point. From there onwards, we should not increase the estimators. So this is what is the technique called as boosting. So boosting is a technique where we are going to give our entire data set with to the one particular model. So the model is going to be trained with 70% of records, and the rest of the 30% of records, it is going to be tested. Out of that, whatever may be the samples that were classified wrongly will be given high priority. And in the next level, along with the original training data, this unclassified or not properly classified records will also be given as training to the model. So our intention is that even though at one level, if the record was not classified properly, it should be classified after third or fourth iteration. That is the intention behind boosting. That is why this model is also called as boosting, because you are boosting the efficiency of the model. So clear. Then the next case is nothing but stacking. It is one kind of example we have seen in the last class. Because I am explaining all these kind of things with very simple examples, you can do the same kind of coding on any kind of data sets. But it will take some kind of, it will take some more time. If the data set is very huge, it will take much time to execute all these programs. So here also I am taking the same kind of breast cancer data, because our intention is that in this particular FDP, we are mainly concentrating on healthcare applications. That is the reason why I am importing a data set called as breast cancer. So in this case, these are the models. I already told you that in case of stacking, initially whatever may be the data set we have to divide the data set into groups or chunks. So each and every chunk will be given to one particular model. Here I am using random forest, I am using logistic regression, and I am using some other kind of thing, linear SVC and multilinear classifier, MLP classifier. Because here what I am doing is that I am using two models. One is linear SVC, support vector classifier, and one is nothing but multi-layer perceptron classifier. These are the two classifiers which I am using at the initial level. So whatever may be the data I have to divide the data set into two parts, training as well as testing data. Out of the training data, I have to divide that entire data set into two parts. One part will be given to linear SVC. The second part will be given to MLC classifier. And whatever may be the classifications that were done with these two models will be maintained in a data as a data set. That data set we are going to give to a model called as a logistic regression. So here you can take any kind of models, but here I am considering three models, because why I have considered random forest, I will explain at a later stage at the end of this particular program. So that is the reason why mainly we are considering three models. One is linear SVC, the second one is multilinear classifier, multi-level MLP, multi-layer perceptron classifier, and the third one is logistic regression. So here these two, linear SVC and MLP classifier, are being used at the initial level or base models. These are the base models, and logistic regression is my meta model, because I have shared you the PPT in the last class. So whatever may be the data set we have to divide the data set into two part, training as well as testing, and we will keep the testing data set as aside. But whatever may be the training data we are going to divide that into two chunks or two groups. One group we are going to give it to linear SVC, and the second group we are going to give it to the MLP. Once after training the models with that particular data set, we are going to test those two models with the remaining 30% test data. So whatever may be the outputs you are going for the test data, we will maintain all the records in a table. That table we are going to give as an input to the logistic regression. So because here also it is a combination of two models. One is base model and the second one is meta model. Whatever may be the predictions that were not done correctly by the base models, it will be rectified by the meta model. That is the intention behind this. I will execute this particular thing. So it is executed here. See, I am using two things. One is SVC and the second one is MLP. So these are the two base models. Here see, these are the two base models, whereas this is the meta model, because this is the stacking classifier. because we have to use 2 models. No, there is no restriction that you have to use only 3 models. You can use 100 models. But out of that 100 models, 99 models you have to use as the base model. 1 model you can use it as a logistic regression. Because mostly I am using this particular for a classification problem. So because in case of breast cancer, we are having only 2 outputs, benign or malignant. So that is the reason why we are using a classifier kind of thing. So here simply in order to execute very fastly, I have considered only 3 classifiers. Out of the 2 classifiers, SVC as MLP will be used as the base level classifiers, and this logistic regression is going to be used as the main meta classifier. Even though the name consists of logistic regression, but this logistic regression is mainly used for classification, whereas linear regression is mainly used for regression. So I have executed this particular block also. Then I am going to divide my data set into train as well as test. So I am going to divide my data set into train as well as test. After dividing my model into train as well as test, I got an accuracy of, please see that here it is the accuracy. The last level is the accuracy with the stacking model. So I got an accuracy of 98.6. So with ensembling technique, that is called as stacking. With the stacking ensembling technique, I got an accuracy of 98.6. And here, please see, I am going to use if you use a single model, what will happen? Please see. If you are using the models individually, because here it is only linear SVC, because I am not using them in the stacking model and I am using them in an independent manner. Instead of executing the same kind of program with 3 models, 2 models in the base level and 1 model in the meta level. So the base models are linear SVC and MLP, and the main model, meta model, is nothing but the logistic regression. If you go in that way, that process is going to be called as stacking, and the accuracy you got is nothing but 98.6. But if you execute this particular model with 2 independent models, one is linear SVC and the second one is MLP. That is what I am doing here. If you execute the same program with linear SVC, your accuracy will be 97.2. So, and if you execute the same program with only MLP, the accuracy will be almost similar to your stacking model. Sometimes it may be reduced and sometimes it is almost equal to your stacking. So this is the way in which we can do the comparative study. You can do the experimentation with individual models, and at the same time you can do the experimentation with the stacking model. Mostly in most of the cases, we are going to get more accuracy if you use stacking models. Is it clear or not? So individual models, they are giving an accuracy of 97.2 and 98.6, and overall accuracy is almost similar to your MLP model. But most of the cases, it is the case where we got similar, but mostly the accuracy is going to be increased if you are using stacking models. So this is the advantage of stacking, bagging, and boosting. So mostly here, whatever may be the data set I have considered is very less data set. It consists of nearly records less than 1000. But mostly whenever we are doing the research and we are applying these particular models on some kind of things like brain tumor data set and fake news detection data sets, these are the data sets, and stock market data set where we have lakhs of records. In such case, definitely the stacking model is going to give more accurate results than the independent models. Even though it is stacking, it is boosting, or it is bagging, you are going to get most optimal results with the help of ensembling technique than the individual model. That is the reason why I am going to suggest all the researchers, if your data set consists of more number of records, please always try to use the bagging, boosting, and stacking techniques, and these techniques are going to be called as ensembling technique. In this case, please don't forget to use 2 classifiers. One is voting classifier and the second one is average classifier. Voting classifier is a classifier which is going to be used for the problems of classification, and the second one, that is nothing but average classifier, is going to be used for the problems like regression. So please select whether your problem is related to regression or classification. I already told you the difference between regression and classification in the last class. Classification is a kind of problem where we are having the records which are discrete. Classification we can done where the records or where the output is discrete. But in case of, we can use regression where the output is continuous. When your output is continuously changing with respect to time, that data is going to be called as a sequence data. Because when you are doing the problems related to stock market analysis, weather prediction analysis, where the output is going to change with respect to the time, in such case, definitely you have to go for regression. If your output is stacking, whether the patient is having a breast cancer or not, or whether the patient is a diabetic or not. So these kind of things can be predicted with the help of classification. Okay. So at the end, we will see any kind of queries related to this particular two programs. But today I have to start with another topic that is called as an optimizer. So give me 2 minutes time. I will share another window and there we will discuss about this particular optimizers. So this is simply a pure empty Word document. So here in this case, I want to prove something. Before going to discuss about optimizers, first of all, you should know what is gradient descent. Because I want to do the proof for this particular gradient descent, and I will apply this particular gradient descent on one particular problem that is called as either OR gate or AND gate. Then you will know how to adjust the weights in case of this particular back propagation. Because optimizers mainly works on the principle of gradient descent. Because optimization here, the meaning is that we have to do the optimization of loss. So optimization of loss means we have to reduce the loss. So that is the major intention behind this. In order to reduce the loss, we have to do the weight adjustment. In case of artificial neural network, how the weight adjustment is going to be performed, I will explain with a simple example. But we can explain on a very big example. But if I take a very big example, it will take nearly 1.5 hour time to solve the problem. In order to avoid that particular problem, I am going to solve this entire problem with one particular example. So what I will do is that I have a neural network. Anybody knows how deep learning works? In deep learning there are two different kinds of models that are available. Initially, the model which is available is nothing but perceptron, and the second model is nothing but multi-layer perceptron. So perceptron is the model in which we have only two layers, input layer as well as the output layer. So input layer as well as output layer. If a neural network consists of only two layers, one is input layer and the second one is output layer, that neural network is going to be called as perceptron. And MLP is nothing but this is the machine learning or deep learning network where you have more than two layers, means input layer, hidden layer, and then output layer. So what actually happen is that this is your input layer and this is your output layer. This is going to be called as your perceptron. And this is the case, this is your input and this is your hidden layer, whereas this is your output. This kind of neural network is going to be called as your MLP. So what is actually we are doing with this NLP as well as perceptron? Anyhow, the intention is that suppose initially when they have developed these neural networks, they have tested all these neural networks on gates, logic gates, because almost all the neural networks works properly on the gates properly. But the main disadvantage what we got is that, so almost all the neural networks are proved with help of perceptron. Initially, they have tested AND gate, OR gate, NOT gate. These are the primary gates. These gates they can able to solve, or these gates they can able to design with the help of, for these gates, either AND gate, OR gate or NOT gate. For these three gates, they can able to create a perceptron, means they can design a neural network with which they are going to get the output. So correctly. So, but if in some cases, if they didn't get the output properly, what they will do is that they have to do the weight adjustment. I think everybody knows that deep neural network is a neural network which mimics the characteristics of human brains. So it simply mimics the characteristics of human brains. So in our brain, whenever we are doing some kind of task, whether we are smiling, whether we are crying, whatever the task we are doing, everything we can do with the help of only one thing, that is nothing but neurons. So with the help of neurons only, we could able to do all the tasks what we are doing right now. If you are smiling, means definitely in your brain there will be some 10,000 or 20,000 neurons should activate as a network. Because of that particular network only you could able to smile. Otherwise, it is very difficult for you to smile. The same intention they have applied to design a deep neural network or deep learning. In this case, in order to perform a particular task, if you want to design a neural network, definitely you can design with the help of neurons. The similar kind of thing they have started by designing the neural networks for AND gate, OR gate, NOT gate, because these are the simple problems. So initially they have designed neural networks. So for the problems like AND or NOT gate. So initially what happened is that they are designed two different kinds of networks. The first one is perceptron. Perceptron means you have two layers. One is the input layer and the second one is output layer. These perceptron works very effectively for the kinds of gates like AND or NOT. But it fails to work properly on one particular gate that is called as exclusive OR gate. So that is the reason why for exclusive OR gate, they have designed a neural network called as multi-layer perceptron. In case of multi-layer perceptron, we are having three different kinds of layers: input layer, hidden layer, and then output layer. So I will explain you very clearly. So why this particular problem was not satisfied for exclusive OR gate? I think everybody knows the standard truth table for exclusive OR gate. In case of exclusive OR gate, if both the inputs are 0, your output will be 1. If your input is 0, 1, sorry, if both inputs are 0, your output will be 0. If the input is 1, 0 or 0, 1, your output will be what? 1. And if the both inputs are 1, your output will be what? 0. So this is the truth table of your exclusive OR gate. Whereas coming to the case of AND gate or OR gate, if it is the case of AND gate, then your output will be 0, 0, 0, 0, 1, 0, 1, 0, 0, and 1, 1, 1. So in this case, what will happen is that similarly like exclusive OR gate, OR gate, 0, 0, 0, 0, 1, 1, 1, 0, 1, 1, 1, 1. So these are the truth tables of AND gate, OR gate, and exclusive OR gate. See one thing, I will draw a diagram here. So I will draw a diagram here. So because these are the two problems or these are the two gates which can be constructed with the help of a perceptron. Because everything we are going to design with perceptron, because the perceptron is having only two layers, input layer and output layer, so that execution time is very less. That is the reason why for all the gates they try to design with the help of perceptron. But unfortunate thing is that they can able to design it for all the gates except exclusive OR gate. I will tell you the reason behind this. Suppose here I am drawing this on a 2-coordinate axis system where this is my origin. So this is my x-axis and this is my y-axis. This point I will consider it as 1. Here this point I will consider it as 1. What are the coordinates at this particular point? This is 0, 0, whereas this is 1, 0, because x-axis value is 1, y-axis is 0, and this is called a 0, 1. X-axis value is 0 and y-axis value is 1. And this is the point which we are going to call it as 1, 1. Please see here very carefully. What will happen, I will write here. If the first I am checking for AND gate. Please be with me for 2 minutes. First we are checking with AND gate. In case of AND gate, if the input is 0, 0, input is 0, 0, what is your output? 0, right? 0 here. If your input is 0, 1, 0, 1, what is your output? It is 0. I will write with another pen. Your output is 0. Here also your output is 0. If your input is 1, 0, what is your output? It is also 0. If your input is 1, 1, your output will be what? 1. All the three values are zeros, whereas this value is 1. What is the advantage is that if I draw a straight line like this entire coordinate system is going to be divided into 2 parts, where one part consists of the value which is 1, the other part consists of all the values as 0. Because this is the problem which is going to be called as a linearly separable. Linearly separable means after drawing a single straight line, whatever may be the regions we are getting, the regions will consist of same kind of output. This is for AND gate. Similarly, I will draw the same thing for OR gate. So OR gate. If your input is 0, 0, your output will be what? Your output is 0. If your input is 0, 1, your output will be 1. If your input is 1, 0, your output will be 1. And if your output is 1, 1, then your output will be 1. So if I draw a straight line here, the other part of the line consists of all the values 1. And here the values, one side of the line consists of 0. The other side of the line consists of all the values are what? 1. Means it is also linearly separable. That is the reason why we can design a single layer perceptron for both AND gate as well as OR gate. Is it clear or not? So whenever you can separate that entire coordinate system into 2 regions, so with the help of a single straight line, that particular problem is going to be called as linearly separable. That is the reason why both AND gate as well as OR gate are linearly separable. Now we will check the exclusive OR gate. What will happen? If both the inputs are 0, what is your output? 0. If your input is 0, 0, 1, then your output will be what? 1. If your output is 1, 0, then if your input is 1, 0, your output will be 1. If your input is 1, 1, your output will be what? 0. If I draw a straight line here, what will happen? Please tell me. This region consists of 0, but this region consists of 3 values which are not same. Similarly, if I draw a straight line here, what will happen? This particular region consists of only one value, that is 0. The other part consists of values which are 1, 0, 1, because these are not same. That is the reason why this particular problem is not linearly separable. So that is the reason why your single layer perceptron will not give proper output for your exclusive OR gate. That is why they have developed an architecture which is called as multi-layer perceptron in case of exclusive OR gate problem. So single layer perceptron or single layer neural network, to do one thing, perceptron can also be called as single layer neural network, because mostly we will never consider input as one layer. We will never consider input into consideration. That is the reason why perceptron will be always called as a single layer neural network. So whereas the other one is going to be called as multi-layer neural network, which will have more than two layers: input layer, hidden layer, and then output layer. Later on, we have developed deep neural networks where we'll have multiple number of hidden layers. So before going to discuss about improperly about the, before discuss about in depth about this particular gradient descent problem, first of all, I will discuss about one thing. So please be with me for some time. So this is an OR gate problem. So where I have two inputs, this is my input layer and this is my output layer. One thing you please remember and keep in mind that, so whenever we have a neural network, suppose, see, this is an architecture which is similar to your brain. And in brain, we have so many number of neurons. Whatever may be the neurons we have, each and every neuron will have a weight. And your neuron can accept the input only up to that particular weight. Once it crosses the weight, your neuron will be bursted and it will enter into a new state called as mentally disorganized state. Similarly, when we are designing a neural network, we have to give one weight to each and every neural network. It is going to accept the weight only up to that extent. Once it crosses, the neural network or the neurons will not accept the weight. That is the major thing we need to keep in mind. So every time whenever you are designing a neural network, you should have two things. One is input and the second one is weight. Each and every input is going to contain one weight, and that particular neuron is going to accept the weight only up to that particular extent. Suppose here I am drawing a neural network called as XY. My inputs are A, B, and my output is Y. If my inputs are 0, 0, my output will be 0. I am writing for OR gate. 0, 1, 1, 1, 0, 1, and 1, 1 is what? 1. So actually what is back propagation or gradient descent? Because gradient descent is the key factor behind this particular optimizers. So optimizers, we have the principle of gradient descent. So the first optimizer itself is gradient descent, and the second one is stochastic gradient descent. There are so many optimizers that are available in the market. RMS prompt optimizer, ADA grad, ADA delta, ADAM optimizer. There are so many optimizers are available in the market. All these optimizers are simple modification of the basic optimizers. That basic optimizer is nothing but your stochastic gradient. So if you do some modification to stochastic gradient, it will be converted into another optimizer. The basic intention of this optimizer is to do the weight optimization. So, but after completion of this particular problem, you could able to know what is actually optimizer. So what actually my intention is that, suppose this is an exclusive OR gate, and here these are my two inputs, and each and every neuron will have a weight called as, here I am taking this as 0.6, 0.6, because each and every input consists of what? A weight. So sometimes we will add one thing that is called as bias. Here I am not writing bias. So bias is the one which is going to act as an offset. When your neural network is not going to produce the appropriate output, then we will call this bias. Suppose when you are studying your intermediate, you have done an experiment called as simple pendulum, where we need to get the acceleration due to gravity as 9.8. But most of the things we will never get 9.8, we will get 9.76, 9.77. In such case, you have to add 0.04 to make this as 9.8. That is what is called as the bias. So you can do the same kind of problem with bias, but I'm not doing this with bias, because if I use bias, the calculation will increase. So that is the reason why I am considering a simple neural network where my weights are W1 is equal to 0.6 and W2 is equal to 0.6. And my inputs are these. These four are my inputs. One thing is that here after giving the input, you are expecting some output. If you give 0, 0, what is your output? 0. That whatever may be the output you are expecting, that is called as target. So after giving the inputs with this particular weights, if you get the proper output, then there is no problem. If you are not getting the proper output, then we need to come back to the previous level and we have to do the weight adjustment. Because if you have multiple levels, Suppose if I have a neural network where I have five layers, input layer, 3 hidden layers and 1 output layer. In such case, definitely what I have to do is that whenever I'm not getting the proper output at the output level, I need to come to the previous level, do the weight adjustment, and then again I need to come back to the previous level, I have to do the adjustment. Again, I need to come back to the previous level, I have to do the adjustment. So again, I need to come back to the previous input layer. Then up to that, I have to do the weight adjustment. And after doing the weight adjustment, again, I need to move in the forward direction. Again, I will check the output. In the second iteration, if I get the output, then there is no problem. In the second iteration, also I am not getting the proper output. Again, I have to do the same kind of back propagation. Again, I need to come back to the previous level and do the weight adjustment. This process I have to repeat till I get my proper target output. Is it clear or not? So this is what is called as back propagation. So for doing this back propagation, we are going to use an algorithm called as gradient descent. I am using an algorithm called as gradient descent. So suppose we will check here. If in this particular case, what I will do is that I will keep one thing, that when you are designing a neural network, you require 3 things. One is the input, second one is the output, the third one is the target. Target is nothing but threshold. The third one is threshold. If your input is less than, but here I am taking a threshold, you can take any threshold, no problem. Based on the threshold, you can design your neural network. I have a threshold that I am keeping my threshold as 1. If my output value is less than 1, I will consider it as 0. If my output value is greater than 1, I will consider it as 1. There is no restriction that you have to keep only this particular condition. You can write any of your condition, no problem. But for my sake, I am taking that if my output is less than 1, I will consider it as 0. If it is greater than or equal to 1, I will consider it as 1. So is it clear or not? So in this case, I will test. Please, what is my first output? Before that, you have to know one more thing that is called as activation function. What is activation function? Activation function is simply the multiplication of input into weight. Suppose I will write like this, I equal to 1 to n, wi xi. But here in this case, how many inputs you have? 2 means I equal to 1 to 2, wi xi means w1 x1 plus w2 x2. This is your activation function. This activation function will be compared with the threshold. If the output of this activation function is less than the threshold value, your output will be 0. Otherwise, your output will be what? 1. So we will check one by one. Please come whether we are going to get the output or not. So here I will write. What is my first input? 0, 0. My first input is 0. So this is x1, this is x2. x1 equal to 0, x2 equal to 0. So x1 w1 means 0 into 0.6 plus 0 into 0.6. Is it clear or not? So 0 into 0.6. This is 0, this is 0. Overall equal to what? 0. It is less than 1. So your output will be what? 0. You are getting the proper output or not? Yes, done. Now we will check the second case. x1 equal to 0 and x2 equal to 1. This is 1. So please check, write the case 0 into 0.6 because we have to multiply input into weight plus 1 into 0.6. So this is 0, this is 0.6 and your output is 0.6 which is less than 1. So your output is what? 0. But what is your target output? 1. Here in this case, your target output is 1, but your obtained output is 0. You got an output called as 0, which is called as an obtained output, but your target output is what? 1. So you are not getting your desired output. So then what you have to do? You have to go to the previous level and do the weight adjustment. How to do the weight adjustment? I will explain. Please be with me for some time. Now check the third input. Here x is equal to 1 and x1 equal to 1 and x2 is equal to 0 because my input is 1, 0. So 1 into 0.6 plus 0 into 0.6. This is what? This is 0 and this is 0.6. So your output is 0.6 which is less than 1. So equal to what? 0. You are again getting an output 0 but your output is what? 1. Your obtained output is 0 but your target output is 1. You are not getting the proper output. So that is the reason you have to come back to the previous level and do the weight adjustment. So we will do the weight adjustment. Please wait, give me 1 more minute time. And the last input is nothing but 1, 1. So means 1 into 0.6 plus 1 into 0.6. So 0.6 plus 0.6, 1.2, which is greater than 1. So your output will be what? 1. In this case and in this case, you got the proper output. But for these two cases, you got an output called as what? 0, 0 instead of 1, 1. So please see what is your output? 0, 0, 0, 1. If both the inputs are 1, your output is 1. Rest all cases, your output is what? 0. Means you are getting an AND gate, but you are trying to develop a neural network for OR gate. So this is the problem which we are facing during the design of our neural network. In order to solve this problem, we have to use a technique called as gradient descent. That gradient descent is nothing but your optimizer. So that gradient descent technique is the technique which was basically used in the design of optimizers. Please see, I will show you two programs, how your output is going to be changed with respect to the optimizers. But prior to that, please give me 10 more minutes time to prove this particular problem. Is it clear? So here, I think everybody got the problem. We are trying to design an OR gate with a neural network, but I am going to get a neural network which is for AND gate because I am not getting the proper output. So how to do the weight adjustment? In order to do that particular weight adjustment, we have to use a technique called as gradient descent. Again, I am writing the same OR gate problem. So I will prove this one. Give me 1 more minute time. So W1 is 0.6 and W2 is also 0.6. Is it clear or not? So here my input A, B, Y. My input is 0, 0, it is 0. 0, 1, it is 1. 1, 0, it is 1. 1, 1, it is 1. So in order to do the weight adjustment, we have to use a formula called as gradient descent. So that particular formula is nothing but, so weight adjustment. Weight adjustment is nothing but when you are not getting the proper output, you need to come back to the previous level and you have to do the weight adjustment. For doing the weight adjustment, this is your input. So Wi equal to Wi plus delta Wi. This delta Wi is the correction which we are doing in this particular case. Delta Wi is the correction. Correction, why you need to do the correction? Because you are assuming something as your output. That output is called as target output, but you are getting some other kind of output that is called as obtained. So this is your target output and this is your obtained output. If both are same, then there is no problem. Then there is no need for the weight adjustment. Then there is no need for the gradient descent. But in this case, you are expecting something, you are getting something. That is the reason why we have to do the weight adjustment. For doing that weight adjustment, we have to concentrate on this particular component that is called as delta Wi, where delta Wi is equal to minus eta into dou by dou Wi of E. Eta is a learning rate because each and every neural network will have a learning rate. Mostly we will consider this learning rate from 0.1 to 0.5. But I will take it as 0.5 because for my convenience, but most of the researchers, they will use this value from 0.01, 0.02 like that they will use. But for my sake, I am using my learning rate at 0.5. There is no logic behind that. For doing the calculations very simply, I am using 0.5. So this is the formula for the correction. So where eta is the learning rate, dou E by dou Wi. What is it actually means that here Wi means what is Wi? Wi is nothing but the weights what we have in the network. So here we have two networks, two weights W1 and W2. So we have delta dou Wi means we have two weights, one is W1 and the second one is W2. So we have to do the weight adjustment so that it results the reduction in error. It reduces the error because reduces the error means it is going to reduce the difference between target and obtained. So you have to do the weight adjustment in such a way that it has to reduce the error. That reduction of error will be is nothing but your optimizer. Optimizer is going to do the process of optimization by simply making your error at 0. If your error becomes 0, that is the basic intention of your optimizer. The purpose of optimizer is to reduce the weight, it reduce the error. And ultimately, most of the cases, we are going to make that error as 0. If error is 0 means your target and your obtained both are same. Clear? But here one thing I'm going to ask you. So there are two different kinds of derivatives. One is regular derivative and the second one is partial derivative. Here I am going to consider partial derivative. Why I am considering partial derivative instead of regular derivative? Why I should not write like this dE by dWi? Is there any reason behind this? So I am writing here partial derivative but not writing the regular derivatives. Why? Because here we are going to check the error, or we are going to do the derivation of error with respect to multiple weights, not single weight. Here Wi means whatever may be the network I have considered. In the network I have how many weights? 2 weights. I have to do dou E by dou W1, dou E by dou W2. When you are having multiple weights, then definitely you have to do the partial derivative instead of regular derivative. That is the reason behind this. Then we have proved up to a particular extent. Then I want to elaborate this one. 5 more minutes. So dou E by, because I want to show you the execution of this particular code on a particular program. So dou E by dou Wi, where error, what is the formula for error? There is a formula that is defined, that is nothing but delta rule. According to delta rule, the error will be always like this: 1 by 2 sigma d t minus d whole square. 1 by 2 sigma d t minus d whole square, where t minus o, we'll write it as o, because this is target and this is obtained, this is square. So why we are considering square? Because mostly whenever you are going to get the negative values, we will do the square operation to make them positive. Here also, when you are doing the weight adjustment, there is a symbol called as a negative. This negative will always represents the reduction of error with respect to the weight adjustment. So is it clear or not? Up to this, the formula for this error is nothing but 1 by 2 t minus o, target minus obtained. Because the intention here to take 1 by 2 as nothing but whenever you perform differentiation on this, t square, the derivative will be what? 2 into 2. This 2 and this 2 gets cancelled. 1 by 2 into t minus o whole square. When you are doing the derivation with respect to this particular term, so t square, the derivative will be what? 2t, 2 into t. So 2 gets cancelled and you are getting simply t. So that is the intention behind this particular square. So here I will substitute that formula 1 by 2 dou sigma d t minus o whole square. But here what I will do is that dou by dou Wi, bring this 1 by 2 here, it is a constant. This sigma also bring forward. So t minus o whole square. This is what we have to do. I think you will get a question that here we have t as well as o. How we'll do the how we will do the differentiation with respect to Wi. But there is one thing you can see here, how you are getting the obtained output. Please tell me. This is your target, and how you got this 0 obtained? Simply by doing this. Is it right or not? W1 x1 plus W2 x2. We can write like this: sigma I equal to 1 to n Wi xi, or sigma I equal to 1 to 2 Wi xi, means it is W1 x1 plus what? W2 x2. So in the obtained means O, this is equal to O. Your target is 1, but after calculating this, you are getting an output called as what? 0. This is your obtained. So here I can write obtained as minus eta by 2 dou by dou Wi t minus Wi xi whole square. Here you got a term called as W, is it right or not? So do the differentiation with respect to what? Wi. This is the term t square. You are going to get what? 2 into t minus Wi xi. Because what is the derivative of t whole square? Any term whole square differentiation will be what? 2t. And for this particular term, you need to do the differentiation with respect to Wi. Minus of Wi xi with respect to Wi, you are going to get it as what? Xi. This minus, this 2 and this 2 gets cancelled. This minus and this minus will become plus. So plus eta into t minus Wi xi into xi. Is it right or not? So what is Wi xi? I can replace again this with what? Eta into t minus obtained into xi. This is the formula for your delta Wi. So this is the formula for what? Delta Wi. Now what is your weight adjustment formula? Substitute whatever may be the value you got for delta Wi in the formula. So right now your new weight will be Wi equal to Wi plus delta Wi means eta into t minus o xi. Is it clear or not? So this is target, this is obtained, and this is called as learning rate. So please remember one thing, there is a difference between parameter and hyperparameter in case of machine learning and deep learning. So here eta is going to be called as an hyperparameter. So this hyperparameter value, I am considering it as 0.5. Now we will do the same kind of OR gate problem right now after the weight adjustment. So please be with me for 2-3 minutes time. We will finish this problem. So W1 is equal to 0.6 and W2 is equal to 0.6. Right now, please come with me. We have the table here. So OR gate table is I wrote here. If both the inputs are 0, then your output will be 0. The rest all cases, whatever may be the combination of your input, your output will become what? 1. Is it clear or not? Then come. We will do the problem. W1 is equal to 0.6 and W2 is equal to 0.6. So first we will have the input called as 0, 0. So you can do it with first do the activation function 0 into 0.6 plus 0 into 0.6 because W1 X1 W1 X2 W2 is equal to 0, which is less than 1. So your output will be what? 0, 0. For A, B, Y, if your input is 0, your output will be what? 0. We will check the second case where your input is 0, 1. In case of 0, 1, in case of OR gate, your target output is what? 1. But before the weight adjustment, we got the output as 0. Now, how to check this? 0 into 0.6 plus 1 into 0.6. So 0 into 0.6, it is 0. 1 into 0.6, it is 0.6, which is less than 1. Again, you got what? 0. You got the output as 0 because your target output, when it is the case of OR gate, if your input is 0, 1, you have to get 1, but you got it as what? 0. Means your target output and obtained output both are not same. In such case, we have to do the weight adjustment. We have to do the weight adjustment for both the weights. How many weights available? 2 weights available. What is the formula for weight adjustment? Wi equal to Wi plus eta into T minus O by Xi. This is what I have derived right now. This is the formula I derived right now. This formula help you need to take here. Please come down one. So initially I am adjusting the weight W1. W1 because I is equal to 1. W1 is equal to W1 plus eta into T minus O into X1. What is your W1? You already know your W1 is what? Your W1 is 0.6 and your W2 is what? 0.6. 0.6 and initially I told that my eta value is equal to 0.5. Anything you can take, no problem. It is 0.5. T minus 4. Your target is what? In case of exclusive OR gate, if your input is 0, 1, you have to get the target as 1. But you are getting as what? 0. Your target is 1, but you are getting is obtained is 0. So target minus obtained. Target is 1, obtained is 0. Your X1. X1 means there are 2 inputs. Here this is X1 and this is X2. What is your X1? 0. So write here 0. So means you are multiplying with 0, this entire term will become 0. So this will be cancelled and you are left with what? So there is no change in the weight of W1. Similarly, do it for W2. W2 plus eta 2 is 0.5. Your target is 1, your obtained is 0. But here instead of X1, what you need to write? X2. So W2 is 0.6, 0.5, your target is 1, your obtained is 0. And what is X2? X2 is nothing but 1 here. So you write 1 here. So that is equal to 0.6 plus 0.5, 1 minus 0, 1 into 1. So it will be what? 0.5. So your new weight will become what? 1.1. Previously, the weight of your W2 is 0.6. Right now, it became what? 1.1. From here onwards, instead of 0.6, we have to consider the weight of W2 as what? 1.1. Now, check for the second input. What will happen? 0 into 0.6 plus 1 into 1.1. This is 0. This is 1.1. Which is greater than 1. So your output will be what? 1. After doing the weight adjustment, your output becomes what? 1. Is it right or not? So you target is 1, but you got 0. That is the reason why we have done the weight adjustment. After weight adjustment, your output will be what? 1. Now check for the third case. 1, 0. Means here x1 is what? 1. This is what? 0. Please check the third input. Actually, in case of OR gate, if your input is 1, 0, what is your output? 1. Except this particular case, all the cases your output will be what? 1. 1, 0. 1 into 0.6 plus 0 into 1.1. 1 into 0.6 plus 0 into 1.1. That is equal to, this is 0, this is 0.6. 0.6 which is less than 1. So your output will be what? 0. Your target is 1, but you are getting 0. Again, you have to do what? The weight adjustment. We will do the weight adjustment. Come. Weight adjustment. W1 is equal to, that is Wi equal to Wi plus eta into T minus O into X1. This is for W1. What is your W1? There is no change in the W1 for the previous level. So W1 is 0.6. 0.6 plus eta is 0.5. Your target is 1. You got the output as 0. X1. What is X1? X1 here is nothing but your input is what? X1 means your input 1. So simply do this one. So likewise 0.6 plus 0.5 into 1 into 1, it is 0.5, which is equal to 1.1. From here onwards, your new weight for W1 will also be what? 1.1. Again, you have to do the weight adjustment for W2 also in this case. So the weight adjustment for W2 is equal to W2 plus eta into T minus O into X2. W2. Because in the previous level only we have adjusted the weight W2, its value is 1.1, eta is 0.2, 0.5, and T minus O, target is 1, obtained is 0, but X2, what is the value of X2? It is 0. So 0. So 1.1 plus this becomes 0, entire thing becomes 0. So your weight is what? W2. There is no change in the weight W2. So right now WT is 1.1, W1 is 1.1. Please check for the same input. 1 into 1.1 plus 0 into 1.1. This is 0 and this is 1.1, which is greater than 1. So your output will be what? 1. And in the final case, if both the inputs are 1, what will happen if both the inputs are 1? If both the inputs are 1, so 1 into 1.1, 1 into 1.1 plus 1 into 1.1, it is equal to 1.1 plus 1.1, 2.2, which is greater than 1. So your output will be what? 1. Please see you got your proper table for arguing. So this is the way in which we have to do the weight adjustment. So after doing the weight adjustment, if you are getting your target output, means definitely the error is what? 0. So this is what is the duty of your optimizer. So the main purpose of optimizer is to do the weight adjustment so that your error will be optimized. Error will be optimized means your error will be reduced. So this is the main purpose of optimizers in case of our deep neural networks, because optimizers plays a major role in increasing your accuracy in case of deep neural networks. In the last class, we have seen ensembling techniques which are very much suitable for machine learning problems. Here, in machine learning problems, we have used some kind of hyperparameters like estimators, where the estimators is going to tell you how many decision trees you are using. In the similar way, in case of this particular optimizers, so optimizer is also one kind of hyperparameter. Based on the selection of your optimizer, your accuracy is going to be increased. I am going to show you what are the accuracies with different kinds of optimizers. And there are so many optimizers that are available in the market, and based on your problem, you can design your own optimizers. But it is the time is not sufficient. Otherwise, I could explain each and every optimizer with the formula. Because each and every optimizer, there is a small fraction of change. Because when we are doing the research, we will always consider the research which was done priorly to us. That is nothing but our literature. And whatever may be the work done by some other person, we will do some slight kind of modifications in order to increase the efficiency or accuracy of the model. In the same way, there are some other optimizers that are available in market. Whatever may be the optimizers that are available, so they are very much similar to this gradient descent optimizer, but there are slight changes in the formulas. In some optimizers, the learning rate is constant. In some optimizers, the learning rate will change with respect to time. Even we are changing the learning rate dynamically in case of some optimizers. But for some optimizers, the learning rate is constant. So I will write some kind of optimizers which we are using for different kinds of problems. So there are so many optimizers that are available. The first one is nothing but gradient descent. The first one is gradient descent. The second one is nothing but stochastic gradient descent, SGD. The third one is nothing but ADA grade optimizer. The fourth one is nothing but RMS prop optimizer. And fifth one is nothing but ADAM optimizer. So these are the familiar optimizers that we are using in case of deep learning in order to increase the efficiency of a particular model. So these are the different kinds of optimizers that are available. So I want to conclude one thing here, that after this I will show you two codes. I will show you the code of this R gate problem also, how the weight adjustment is going to be done. I will show the code for that also. So here there are mainly 5 optimizers which we are, so many are there, ADA delta. There are so many optimizers that are available in market. If you can click in Google, or if you search in Google that optimizers, then you are going to get so many optimizers. Use any kind of optimizers that is suitable for your problem. But the major intention of optimizer is to optimize the loss, optimize the error. Optimize the loss or optimize the error means you have to reduce the error in such a way that the error becomes 0. Our intention is that if the error becomes 0 means whatever may be the output you are expecting, you will get the same output. As long as your target and obtained outputs are same, your error is 0. If your target and obtained outputs are not same, there will be some error, and you need to do the process of gradient descent to make that error as 0. That is what is called as optimizer. So clear? So we'll go ahead with some kind of execution of program. Give me 1 minute time. I think that everybody could able to see this particular code. So this is a code which is called as perceptron, which actually we have done for gradient descent. So here I wrote the program name as perceptron OR gate. So this is the code which we can execute the OR gate problem. So with the process what I have explained, nothing but gradient descent. Suppose here in this case I am using NumPy. So NumPy and pandas, so directly you can use that library function. And then here we are writing the feature. Here features, there are some kind of vectors we are having. These are nothing but, please see, 0, 0, 0, 1, 1, 0 and 1, 1. These are nothing but your inputs. And gate we have 4 inputs, 0, 0, 0, 1, 1, 0, 1, 1. And similarly here in this case you can see that this label is nothing but your output. If your input is 0, 0, your output is 0. If your input is 0, 1, your output is 0. 1, 0, it is 0. 1, 1, it is 1. Because I think here I wrote the output of AND gate. I will change it. OR gate means if both the inputs are 0, then your output will be 0. The rest of all cases, your output will be what? 1. Here I am giving my weight functions. Weight, I have taken 2 weights, you have already seen. My weights are W1 and W2. And my threshold is 1. Because if the output what I am getting is less than 1, my output will be 0. Otherwise, my output will be 1. If it is greater than 1. So learning rate. Learning rate means eta. Eta is equal to 0.5. Because I have shown you whatever the inputs I am considering before doing the gradient descent. And here I am considering 3 epochs because I need to do the back propagation till I get the output. Instead of keeping this, because we know that after second iteration, we got the output. That is the reason why I will change my epoch as 2. Epoch means number of times I have to run this model. Epoch is also one kind of hyperparameters. Epoch is also a hyperparameter. So here I am running for loop where this chair runs from 0 to epoch. 0 to epoch means 0 to 2 means here we have epoch 2. 0 comma 2 means this particular loop will run for 0 as well as for 1. Is it clear or not? So first I am printing the epoch j, epoch 0. I will execute the program and again I will come back for epoch 1. I will do the same kind of program. Here x0 and x1, because I have shown you that we have two inputs x1 and x2. Instead of x1 and x2, I wrote here x0, x1. So what is this particular thing? So sum underscore unit. This can be nothing but your activation, because we are doing w1 x1 plus w2 x2. Because here instead of x1 I wrote x0 and x2 I wrote x1. So that is the reason why w0 x0 and w1 x0 x1. Whatever the value you got, if this value is greater than threshold, then you have to fire 1. Because if it is greater than threshold, your output will be 1. If it is less than, its value will be 0. Otherwise, you need to fire 0. Up to this, I think it is clear. Then what I am doing here is that delta. Delta means we have a formula that T minus O. T minus means target minus obtained. Target is nothing but actual and fire means obtained. With this difference, you need to find out the difference with delta. Because here in this case to weight adjustment, please see the weight adjustment. W not equal to W naught, because we have seen that W1 is equal to W1 plus eta into, eta means learning rate, into T minus O into X0. Because here we are considering the input as X0 and X1. So W0 is equal to W0 plus delta means what? T minus O, actual minus fire. T minus O into learning rate eta into X0. Similarly, for weight adjustment of second weight, W2 there I wrote, but here it is W of 1. Equal W of 1 plus delta means T minus O, target minus obtained means actual minus fire, into learning rate eta 0.5 into W1. So this is what is called as weight adjustment. Whenever weight adjustment is needed, it is doing the weight adjustment. Because see, if you execute this particular program, it is taking some 1 or 2 minutes time to execute. It got executed. Please see the output. We have first epoch 0. If your input is 0, 0, what is your output? Your target is 0, you are getting 0. Prediction is 0. No problem. You are up, because this is for 0, 0, 0, 1, 1, 0, 1, 1. Because your input is 0, 0, your target is 0 and your obtained value is also 0. For 0, 1, your target is 0 and your obtained is 0. For 1, 0, your target is 1, your obtained is 0. For 1, 1, your target is 1 and your obtained is 1 during the first epoch. After the completion of first epoch, we are executing the second epoch where we are doing the weight adjustment. After doing the weight adjustment, your target is 0 for 0, 0 and your obtained is also 0. For 0, 1 input, your target is 1 and your obtained is 1. For 1, 0, your target is 1 and your obtained is 1. For 1, 1, your target is 1 and your obtained is 1. Please see, after second iteration, you are going to get the output as C. In case of OR gate, if both the inputs are 0, your output is 0. In rest of all the cases, your output will be what? 1. The same thing you can also do it for AND gate. So because simply instead of writing this one, AND gate means what? If only the both inputs are 1, then our output will be 1. The rest all cases, your output will be what? 0. In this case also the weight adjustment will be done. Please check your output. See, because here there is no requirement of the second iteration. Because there is no weight adjustment is required. That is why during the first epoch only you got your output. There is no second epoch is also required for AND gate. So this is the way in which we can execute the thing where we are doing the weight adjustment. This is only for weight adjustment. There is no optimizer in this case. But the optimizer, what we have used is nothing but gradient descent. So this is the first optimizer that was actually developed. Based on the formula of this gradient descent, There are several variations of other optimizers are available. I will show the other optimizers with one more example. So I think everybody could able to see my screen here. It is a very simple example where I am going to build my neural network. Here, in order to execute this particular program, I require these kind of standard libraries function from Python. So I'm importing TensorFlow, I'm importing Matplotlib because I'm plotting some kind of curves. That is the reason why I require Matplotlib. And then I'm using NumPy. If possible, you can also use Pandas. You have to use Keras because I'm downloading the data set from Keras itself. Because there are some data sets available in Keras in Python library. Straight away, I'm downloading one data set from Keras. So here, see, I am taking xtrain and ytrain because I have two kinds of data. One is train data and the second one is test data. That train data and test data I am downloading from Keras dataset, where my dataset is M1IST dataset. So in case of M1IST, there are two familiar datasets are available. One is digit dataset and the second one is fashion dataset. M1IT digit dataset and M1IT fashion dataset. In case of M1IST dataset, there are 70,000 images are available in case of digits. Please remember one thing. In case of M1IST dataset, there are 70,000 images are available and all the images are consist of numbers from 0 to 9. So 0 to 9 numbers, there are 70,000 images are available. 0 to 9 means how many numbers? 10 numbers. Means you need to classify from 0 to 9. So means altogether 10. So we should have 3 layers at least. One layer is the input layer and the second one is the hidden layer and the third layer is the output layer. We should have at least 3 layers. One is the input layer, the second one is the hidden layer and the third layer is the output layer. Because I am doing a simple kind of neural network which is called as artificial neural network. You can do the same problem with any number of hidden layers, but I am executing with only one hidden layer because I am paying more attention on the optimizers, not on the hidden layers. So here what will actually happen is that there are 70,000 images. Out of that 60,000 are for training and 10,000 for testing. And one more is that in this particular case, you have 70,000 images which consists of images of digits from 0 to 9. Means altogether 10 digits. Means you have 10 classifications. That is the reason why your output layer should consist of 10 neurons. This is the basic logic. Your output should contain 10 neurons. But there is no limit on the number of neurons in the hidden layer. Your hidden layer may consist of 32 neurons, 64 neurons, 60 neurons. It is your wish, no problem. But coming to the case of number of neurons in the input layer, we have altogether 3 layers: input layer, hidden layer, and then output layer. Output layer consists of, because it is going to classify among 10 numbers. So that is the reason why it should consist of 10 neurons. Whereas the input layer consists of, because in this case, we are going to consider each and everything as an image. Because it is an image, because I will execute, then you will see how the image will be. Then I will explain you. In this case, whatever may be the images we are considering from the data set, each and every image is of size 28 by 28. So 28 rows and 28 columns. If you multiply this 28 into 28, its value will be 784. So means in case of this particular neural network, the input layer should consist of 784 neurons. Because as the size of each and every image is 28 by 28. Because I'm using this data set, please see. The third step is nothing but length of xtrain. The training images are 60,000. Next to length of testing images. The testing image size is what? 10,000. Now I am seeing what is my image here. So my image is here what? 5. Because image size is what? 28 by 28. So it is going to show the entire numerical data. Because each and every block is 28 because it is one particular row. Likewise, how many rows I have? 28 rows. Because the input size is 28 by 28. So 28 into 28 is nothing but 784. So 784 neurons should we have in the input layer. We should have in the input layer. And the hidden layer, there is no restriction. You can keep any number of neurons. But at the output layer, we are going to classify among 10 images. So that is the reason why we should have 10 neurons. So please see the X shape. Shape means it is having 28 rows and 28 columns. Because here I am displaying the 50th image. Because I have nearly 70,000 images. Out of that, I am using 60,000 images for training. Out of that 60,000, I am displaying an image which is 50. If I display the image, please see the image. The image number is what? 3. Likewise, we have nearly 70,000 images. Out of that 70,000 images, 60,000 for training and 10,000 for testing. So here in this particular image, the image size is of 28 by 28. So it is the size of the image is 784. 784 neurons are required to represent that image. Then this is the shape of the training. Training shape means 60,000 images we are using for training, and each image is of size 28 by 28. Testing size. 10,000 images we are using for testing, each of size 28 into 28. Then the next step is very, very important. This is for the flattened. What is actually the meaning of flattened means? Whatever may be the image we have, this image data we are getting in the form of what? Matrix. Matrix means rows as well as columns. It is nothing but a square kind of thing. But we cannot give this square kind of thing to as an input to a neural network. That is the reason we have to keep all these 784 values, sorry. All these 784 values either in a one particular row or in a particular column. So for keeping all these 784 values in one particular column or in one particular row, we have to do an operation called as flattened. So this is the flattened operation. Then here I am doing the normalization operation. Normalization means here we are having the values from 0 to 255. So that we are converting this 0 to 255 to 0 to 1. So I am keeping my entire range from 0 to 1 instead of 0 to 255. This is what is nothing but normalization. Come to this. This is the place which is very, very important in the case of neural network. Because this is the place where actually I am developing my neural network, building my neural network. So model is equal to keras.sequential because I am developing a sequential model. Input layer followed by hidden layer, then followed by output layer. Sorry, input layer, then hidden layer, then output layer. So my input layer should consist of how many neurons? Because the size of each and every image is 784. So the size is nothing but 28 into 28 equal to 784. I should require 784 neurons in the input level. And that is in the form of flatten. Flatten with a shape of what? 28 by 28. Means 784 neurons I require at the input level. And at the hidden layer, please see, this is the hidden layer. Dense means hidden layer. So hidden layer means I have how many neurons in this case? 32 neurons. And I'm using an activation function called as ReLU. Sorry, because I don't get that much time to explain about the activation functions. Otherwise, I could able to tell what is the activation function that is best suited for a particular program or problem. So here I'm using an activation function called as ReLU, and this is my output layer. Output layer consists of how many neurons? 10 neurons, because this is the classification where there are 10 classes. So my input neuron consists of 784 neurons. Please see here. Input 784, hidden 32, and output 10. Because you can add any number of hidden layers, there is no problem. And here also you can take 64 instead of 32 or 16 instead of 32 also, there is no problem. I am executing this particular, it got executed. Then I am compiling my model. While compiling, I am considering an optimizer which is called as ADA-grad. I told you there are so many operators that are available. The first one is stochastic gradient SGD. The second one is ADA-grad. The third one is RMS prop. The fourth one is ADAM. There are so many optimizers are available. Here I am using an optimizer called as ADA-grad, and this is the loss function. And there are so many other loss functions are also available. And this is what is nothing but your accuracy. Ultimately, we have to calculate the accuracy and loss using this optimizer. So I will execute this particular problem. And here, please see, I am running it for 5 epochs because I am running this particular program for 5 epochs. What is the meaning of this 5 epochs? Means we are training our model with 5 epochs. 5 times we are training our model. Because by using this ADA-grad model, by using this ADA-grad model, ADA-grad optimizer, so what is my accuracy? Please see. After 5th iteration, my accuracy reaches what? 86%. Simply what I will see that I will change here as SGD, stochastic gradient. Because please see, with ADA-grad, your maximum accuracy is 86 with stochastic gradient. Because you can keep any number of epochs, but here I am executing my program for 5 epochs. This is only, I think it is training accuracy, not testing accuracy. Training accuracy maximum I got is what? 92. Previously it is 86. Right now it is 96, and loss is also decreasing. Please see. Loss is also reducing. Now, instead of ADA SGD, I will write RMS prop. This is one optimizer. The first approach I got 86 with ADA grade. The second one is SGD, I got 92. And the third approach I'm using, third optimizer I'm using as RMS prop, with which I got an accuracy of nearly 97 or 96.90. This is RMS prop. And we are having one more thing that is called as ADAM optimizer. Likewise, there are so many optimizers that are available. You please go through Google and select one optimizer and apply here. So that is the reason why whatever may be the accuracies I got, that accuracy is going to be changed with respect to your optimizer. So the first optimizer that is nothing but ADA grade gave me only 86% accuracy. The second one is nothing but SGD, it got 92. RMS prop, it gives me 96. And the last one, it is nothing but ADAM, it gave me an accuracy of 97%. And finally, I will see the testing accuracy. The testing accuracy of this particular model is nothing but 96.77%. Whereas my training accuracy maximum is 97.88 after fifth epoch, and my testing accuracy is 96.77. As almost the testing data is similar to your training data, we don't have the problem of overfitting. One more point I will tell you that. So if you use neural networks, definitely we will never face the problem of underfitting. If the number of epochs goes on increases, it try to reduce the problem of overfitting also. In neural network, we will never get the problem of underfitting. We will face only one problem that is called as overfitting. Still, that overfitting problem can be eliminated with the help of hyperparameters. One hyperparameter is nothing but epoch. Otherwise, you can also use batch size. So this is a simple example with different kinds of optimizers. So we can use different kinds of optimizers for different kinds of problems. When you are unable to get proper accuracy without optimizers, you please use an optimizer so that you will get proper accuracy. Your accuracy will be always increased with optimizers, because optimizer is always used to reduce the loss. Our ultimate aim with optimizer is to optimize the loss function, optimize the error function, because we can reduce the error by doing the gradient descent operation. The basic for optimizer is nothing but your gradient descent operation. So whatever may be the operators or whatever may be the optimizers we have, in almost all the optimizers we will use this gradient descent. But some parameters will be added, or in the numerator part, or mostly in the denominator part, we will add some operators for different kinds of optimizers. That is the only difference here. So clear, I think with this, I will conclude my session. So I will wait for queries. If any queries, please.
Participants are requested to use the chat box and post your questions in the chat box.
Thank you, sir. Prasad garu.
If any questions, please post in the chat box.
Thank you, sir. Thank you, sir. Thank you, and Rambab garu. Thank you, Naresh garu. I think one thing is that I didn't get more time. Otherwise, I could able to explain this activation functions also. Then it will be more clear about the optimizers. Thank you, and Mahesh garu. Tell me, sir, Naresh garu. Thank you, Bhaskar garu. In case of categorical data. Thank you, thank you. Yes, sir, yes, sir, you can use it. So, but what is that? We cannot say that this particular optimizer is best for a particular problem. So we can use, we have to use in trial and error basis only. Based on trial and error basis, some optimizers will be suitable for some kind of problems. Thank you, Sunita garu. So what is the meaning of kernel here, ma'am? Yes, yes, sir. Otherwise, we cannot do the things. If we cannot convert the categorical data into numerical, we cannot do this. Yes, sir. No, no, sir. There is no risk because in case of that is what the reason I told you that because it never depends on optimizer only because simply we have calculated only W1 X1 plus W2 X2. But the W1 X1 plus W2 X2 should be given to an activation function. So there are different kinds of activation functions that are available. But mostly we will consider only 6 activation functions. ReLU, leaky ReLU, sigmoid, and then tanh, and then softmax, linear activation functions. These are the 6 activation functions which mostly we'll use. But we have 2 different kinds of layers. And one is hidden layer and the second one is output layer. In hidden layer, we have to use only 3 activations which are very much suitable for hidden layers. The activation functions which are very much suitable for hidden layers are nothing but ReLU, sigmoid, tanh. The activation functions that are suitable for output layer is nothing but linear, sigmoid, as well as softmax. When it is the case of multi-class classification, definitely it never depends on your SGD. It never depends on your optimizer. It depends on your activation function. If it is multi-class classifier, please select always softmax activation function. If it is binary class classification, then simply go with sigmoid activation function. That depends on your activation function, not on your optimizer. So, but blindly you can say that here in the code also I wrote that, please see here. In the code also, I wrote here, please see, this is a hidden layer. In the hidden layer, I'm using activation function called as a ReLU. In the output layer, I'm using an activation function called as sigmoid. When you are using a ReLU activation function, whatever may be the output of yours, it will be simply converted in between 0 to infinity. Even though if your input is minus infinity to infinity, it is going to confine that to 0 to infinity. Whereas in case of sigmoid activation function, it is going to be converted from any minus infinity to infinity to 0 to 1. So sigmoid is mostly suitable for binary classification. But whenever you have multi-class classification, definitely you have to use softmax activation function. That is the major thing. That is what I told you, that if I could able to explain you the activation function, this session will be more fruitful, but it will take nearly 1.5 hours of time. Otherwise, one more time we'll meet and discuss about those things. Yeah. My mail ID I'm sharing through mail ID only. Yes, you can use only. Sigmoid you can use whenever there is binary classification. There is no restriction that for some kind of problems you have to use sigmoid. If that particular activation function is suitable for the problem, it is going to give the proper output. Otherwise, it won't give the proper output. So I will show you one more thing. If you add one more layer here, so here what is the whatever may be the accuracy you got, it is of I think 97 or something. If you add one more hidden layer, definitely your accuracy is going to be increased. But there is no guarantee time that every time it is going to use increased. It is after a particular point, you got also saturation about the adding of hidden layers. So almost similar. But some problems adding, so otherwise you can change this one. It will also increase your accuracy. Instead of keeping 32 neurons, you can also keep 64. Likewise, you can do all these things. No problem, sir, Prasad Garu. So my mail ID is no problem, sir. I have videos for all these things which I have explained to my students. If you have any queries or if you want all the videos, I'll share the videos. You please share your mail ID because I have given my mail ID. You please be in touch with that mail ID. I will share the videos because all the videos are available in my drive, so that I'll share the drive. I'll give the drive link. So thank you, Andy. Thank you very much.
I would like to take this opportunity and thank Dr. Srinivas sir. So we are truly grateful to your contribution significantly to this FDP through your valuable insights and engaging presentation. Thank you so much, sir.
Thank you so much, sir.